So now we talk about the matrix multiplication, which is a big concept of this chapter. Now we are going to talk about the determinant of a 2 times 2 matrix, which is another big concept of this chapter. So if M is an arbitrary 2 times 2 matrix denoted by A, B, C, D, then the determinant of it is denoted by that M, which is AD minus BC. So it's the product of this diagonal minus the product of this diagonal. And what does the determinant do? It actually tells you how the area of the grid has changed for linear transformation induced by a matrix. You may not understand a linear transformation and now, but you get know more of it in the later sections of this chapter. But basically, idea is if you have a square of area A in original grid, and then you transform it by a matrix, you actually multiply it by the x and y of the unit vectors, and its determinant is 2, then it means the resultant grid, this square, will actually be 2 times as big as the original. But you don't need to know this point very much. The main thing is that if a determinant of M is 0, then M is said to be singular. You need to remember this word. It may come out in the test. And also, there are some properties of the determinant. So, that of Ka, if you just multiply matrix A by a scalar or number K, then you can actually get K out and square it. So you get K squared that A. And the determinant of a product is the product of a determinant. To calculate the determinant of a product, you just calculate the determinant of the two matrices separately and times together. And the determinant of the identity matrix is 1. So why is all this determinant stuff relevant to you? Well, it is because you need it to calculate the inverse of a 2 times 2 matrix. And the inverse is analogous to the reciprocal of a real number, because you cannot actually divide a matrix by another matrix. So instead, you have to multiply it by the inverse of it. Let's get into it now. If M is a square matrix, in our case it's 2 times 2, then the inverse of it is denoted by M to the power of negative 1. And the inverse is basically if you multiply the two together, so M and M inverse in any order, you get the identity matrix back. So this one is actually a nice property because these two matrices actually commutes. Generally, AB does not equals to BA, but in this special case of the inverse, M inverse is the same as M inverse M, which is the identity matrix I. So this is similar to the reciprocal, where the reciprocal of 2 is 1/2, and if you multiply the reciprocal with the number itself, you get 1 back. So how to actually calculate the inverse of a matrix? Well, it seems strange at first, but actually it's not that hard. If we return to our arbitrary 2 times 2 matrix A, B, C, D, then the inverse of it will be 1 over its determinant and times this matrix. This matrix is what you get if you just switch the diagonal AD with DA and put the negative sign on the other diagonal. So it's AD becomes DA and BC becomes minus B and minus C. But M must be non-singular for it to be invertible. Because if you remember, what singular means is that the determinant is 0, and obviously you can't divide it by 0, so it has to be non-singular. But you may be wondering, why is M inverse such a strange expression? Well, we can verify now. Because from our definition, if we would times it together, we should be able to get the identity matrix back. Now we just do it. This is M inverse. This 1 over the determinant is just a number. We can pull it out, it doesn't matter. And what will remain is this times this. These 2 times 2 matrix together. I have the number of rows of this one is 2 rows. And number of columns of this one is 2 columns. So they can be times together. And the resultant will be these 2 rows times these 2 columns. So we will give you another 2 times 2 matrix. So you can remember your algorithm. The first row, first column of the resultant is the first row of this first times the first row of the second. So this AD plus this B times negative C. So you have AD minus BC. The other one, this first row, second column, will be this first row times this second column, minus AB plus BA. You can actually observe that these two will cancel because A, B are just normal numbers, they are on a matrix. So if you have a minus AB and a plus AB, they will cancel to 0. And this AD minus BC is exactly the expression of the determinant. So if you divide it by itself, it becomes 1. So it's 1, 0, 0, 1, which is the identity matrix. So on your own, you should try to show that the other way, M inverse times M is also equals to identity matrix. And you can actually see that the inverse of the identity matrix is just itself. You can try to work it out on your own to think about it, why this is true. Now you've been wondering again, what is the use of all this inverse matrix? And actually it's useful for you to solve simultaneous linear equations. So in the past, you may have learned how to solve a system of linear equations like this. Actually, you should have learned that. If you don't know how to solve a problem like this, I will be very disappointed in your maths teacher. But actually, there are many ways to solve two linear equations with two unknowns. And in this chapter, we'll approach it using the inverse matrix method. And as a side note, when I say linear equations, I mean the equation only has x plus y or plus 2y. It doesn't have x squared or sine of y or x multiplied by y, that crazy stuff. The x and y, these unknowns, can only be plus together. You can actually recognize this as the equation of the line. That's why it's called linear equations. You can only solve linear equations using the method, not other equations. But now let's get into the matrix stuff. First, you'll notice how the system can be written in the form of this matrix times this and equal to this. Why? Because if you actually work out the matrix product, this first row times this first column is 1x plus 2y equals 3, which is our first equation. And the second one is 4x plus 5y equals 6, which is our second equation. And this corresponds to a general expression of ax equals b, where A is the matrix full of the coefficients of the unknowns. X is a column matrix containing the unknowns, and B represents the constants. So in our example, A is 1, 2, 4, 5, which comes from this 1 and not written out, 2 and 4, 5. It's actually very easy to just pull out the coefficients, but just be careful, it has to be x in the first place and y in the second place. If it's 5y plus 4x, you actually need to switch them around to get into this form. And the x matrix has only one column, that's why it's called a column matrix. It's the variables unknown, x and y. And B is whatever the right hand side is, this constants. So after we converted the system equation into a matrix equation, how do we solve our question originally? Our ultimate goal is to get x and y, which is this x column matrix containing the unknowns. This will be equal to something. When we get in this form, we can know what x and y are by just directly read off this column. Because if two column matrices are the same, their corresponding rows must be the same. So we just read off the rows, so we'll know what x and y are. And that means we need to isolate x on the left hand side. So we need x alone, and we need to get rid of this a somehow. And if you remember in your normal algebra, if you have ax equals to b, what you'll do is actually divide by a on the other side. So you can have x on the left hand side alone. But in the matrix world, it's a bit different, at least in its jargon. That is to say, you need to multiply on the left by A inverse in the matrix sense, so you can get rid of the A. So you do this, and it's actually very important. You pre-multiply, so times it on the left by A, because you know matrix multiplication are order important. If you multiply this A on the right, it won't cancel out with this A on the left, and you won't get this identity matrix back. But anyway, after you do this, you can remember that the identity matrix I just acts as a number 1. If you multiply by it to any matrix, it doesn't do anything really. So you get x on the left hand side alone, and the right hand side is just this. So all we need to do is just multiply b by A inverse on the left. and we assume that A is invertible, this thing has to exist.